What? What's wrong? I think Young said she'll be back in a minute. Okay. Okay. Okay, I think we can continue. So you can finish those at home. Yeah. Yep. Okay. So to start, here is our battery. So we know there's a current going around like this. Okay. So the current is, for example, if I say 2 amps, that means 2 coulombs per second. What does coulomb measure? Charge, yeah. Now, a capacitor is a device that can store a small charge. So a capacitor is something that can take this charge and hold it. No, because in fact it's always something small. Yeah. I can give you an example now in a minute. Can I go down? Yeah? So this is what the capacitor looks like when we draw it. We just draw it as 2 straight lines, like this. So what happens is, the current comes along here, but then it builds up in here, and then it continues. And then what happens is, if you then, I'll draw this again. If you then stop the current, then what happens is the charge that was in here, so this is a charge that builds up, this charge then comes out. I'll give you an example of my cup of coffee. So we can think of this like a capacitor, okay? So imagine I have a tiny little hole here, okay? So what happens is, if I pour lots of water in here, the water fills up, doesn't it? And then once it fills, well, it fills up, but it also comes out the bottom, okay? So I fill this up with lots of water, and fills up, and it's dripping out. But then if I take the water away, is there still water coming out here? Yeah, there'll be water coming out until this is empty again, okay? So this is what the capacitor does. The charge builds up inside of it, and then when you turn the switch off, the charge then continues for a few seconds until it's empty again. Okay? So a capacitor holds a charge. That's what I mean here. A capacitor can store a small charge. Okay. So How do you make a capacitor? Maybe Ibrahim or Hugo, you know what a capacitor is? How to make one? What do you need? How to make a capacitor? No? No? Ibrahim? Who? No? Okay, I'll tell you how to make one. It's very easy to make one. All you need, a piece of copper, and then another piece of copper, and then this distance here must be very small, like for example maybe 1 millimeter, and if possible you can put it inside of a vacuum. So what I mean by that is no air in here. And that's how you can make a capacitor. So it's a very simple machine. So the charge comes along here and then builds up and then continues on through. Okay? Some capacitors can store more charge than other capacitors. So we need a way to measure how much we can store. So this is called capacitance, yes. So the formula we have is Q equals CV. Or if you want actually, I'll write it the other way. Capacitance C, yeah, come on, yeah. Q over V. So if you look, what we can do is, here's our capacitance, and then here's our battery of volt V. So we say we have capacitance equals 1 coulomb per volt, means the capacitor can hold 1 coulomb of charge per 1 volt in the battery, in the power supply. This is called a farad. So 1 farad equals 1 coulomb per volt. Yeah? Which constant is that now? Is that the 4 pi epsilon? It has something related to it, which we'll see in semester 2 when we do electric fields. There is a relationship to that here. Yeah. Okay. So let's have a look at a small example just to get started with the idea. Can I go down? So if I look here, let's say this capacitor is 0.5 farads, and I connect it to, let's say, 100 volts. So I would like to know what's the charge that I get inside the capacitor. So the only formula I have so far is this: C equals Q over V. So what does Q equal? CV, which is 0.5 times 100, which is 50 coulombs of charge. why would you want to use a capacitor? Why might a capacitor be useful? What do you think? True, it could be an emergency power supply, although a battery might be more suitable for that. Good thinking though. Can we think of something else?
Control something turning off, like, I don't know, like turn off completely, maybe like a pause or something.
Yes, if you need something maybe to power down gradually. I'll give you a really, really important example. Right. Don't look at what I'm typing because I want to get a picture, okay? So don't look. No cheating now. Is he? I know he's a dirty cheater. Who's looking? Internet's not connected. Hang on. I told you, he's a cheater. He's a dirty, dirty cheater. Have I got internet yet? Or actually, do I? No, that's just the same as the... let's try that one. There's something... everybody knows it. I know everybody knows this. I'll show it to you now. You can get the picture. It's the internet. Internet's terrible. No good?
Well, you look it up yourself.
Hang on. Forget it. Yeah, I just have to demonstrate it for you. So you know, in a hospital, when sometimes a person's heart stops, they have this machine that they put on their chest. You know this machine? You know the sound it makes?
Yeah.
Yeah. So you hear it. First it charges up, so you can hear it going, charging up, going. This is the capacitor. Okay, so what's happening is when they turn the machine on, the charge is building up inside the capacitor, and then when they put it on the person, then the charge is released. So what they do is they build up a lot of charge and then they release it. Okay, so this is an example. Another example is, if you remember with old cameras, where you press the button, then you have to wait for the flash. Do you know these cameras? The old ones now. So you press the button and you can hear it charging up. But I don't think cameras really do this anymore, or do they?
Depends, I think the hipster ones.
Yeah, if you press the button on your camera, do you get the flash straight away, or do you have to wait for the flash?
I think you can control it.
It's straight away, is it?
You can control it with some cameras. Like some cameras you can say pause the flash.
Alright, but does anybody's camera, when you press the button, you have to wait for the flash?
Yeah, sometimes my sister's camera.
Yeah, so what's happening is the capacitor is charging up. Okay, so I don't have the internet to show you a picture of it, so it doesn't matter. But an example might be with the person in the hospital. So I'll give you that example. So what they have is they have this here, and then they have this here, as you know, and they connect it to a capacitor. And then they connect it to, let's see, it's usually something quite large, 600 volts. And then this is 2 microfarads. So let's work out how much charge builds up here. So you have Q equals CV. That's 2 times 10 to the minus 6 times 600. That's 1200 times 10 to the minus 6. Yeah? So that's 1, 2, 3, 4, 5, 6. It doesn't actually look that big. 0.0012 coulombs of charge. And here, look, we'll put the person's heart in the middle here. There we go. Yeah. So, let me draw you a simple but more accurate circuit diagram. Can I scroll down? So, for example, here is your battery. Now let me get this right. And then here is your capacitor. Yeah, I'll try and draw this as nicely as I can. And then what I'll do is, yeah, here is your, whoops. Okay, and then maybe here is your light or whatever. And then, yes, this is connected here, but it's connected with something like, I don't know, some plastic or something. So there's no current here, okay? It's like some plastic. Yeah. So what I'm picturing here, if you look, is here's the battery, and the current goes like this. And then what happens here? You get your charge, like that. So then this is charging up. Okay? Then, for example, if I move this up, then can you see here these little arrows? If I push this up, what happens? It disconnects. Can you imagine that? If I move this up, this here goes up here, and this one goes up here, and then they disconnect. Yeah? But then, these two connect. So if I just draw it by the side here, if I move it up, it will look like this. Yeah, this is like maybe a light bulb. Huh? And this here is plastic here. So the current doesn't go down, it only goes across here. So then we push it up, so it's up here now. And then we have this one. Yeah, so if I just redraw this.
Oh, the Q is not moved.
What's not moved? No, the Q is not moved. The Q stays, the charge stays here. So what I've done is I've moved all of this up. So this piece falls off, and then this piece here connects. So now what happens is the current now goes this way. So the capacitor discharges, the capacitor releases it. So I'm picturing this like the camera, you know, something like, this is my camera, okay? You press the button down, and then you hear it charging up. So when you press the button down, it goes click, and the capacitor charges up. And then you release the button, so then it goes back up, yeah? And then you can see that now the capacitor releases its charge. So this is just my camera that I imagined, that I made. So in my camera, you press the button, it goes down, and then it starts to charge, and then you let go, so it goes back up, and then you can see that the capacitor now releases its charge. Okay? So it's just my simple little switch. Of course, you know that you would need to put some kind of some kind of spring here, so that it pops back up. Yeah. But I mean, that's the simple idea. Okay. Our capacitor stores charge, so we know that Q equals CV. But if we want to know how much work our capacitor can do when it's fully charged, the formula for how much work the capacitor can do is a half CV squared. So let's go back to the example we had with in the hospital. Let's see how much work can be done here. It's a half CV squared, so that's a half 2 times 10 to the minus 6 times 600 squared. What's that, please? It should be pretty big. 360,000, including even with the 10 to the minus 6?
Sorry,
yeah.
0.36.
Okay, that doesn't sound so much. It's 0.36 joules. So that's how much work the capacitor can do. Can I go down? Okay. So here's our capacitor. How can we make this capacitor hold more charge? Yeah, we have to change something with the distance. What do you think with the distance? Increase the distance? You know what? It's actually not. It feels like if you make the distance bigger, you can hold more charge. In fact, it's the opposite. If you make the distance smaller, you can hold more charge. So if you want to increase the capacitance, then you need to decrease D, the distance between the two copper plates. Now, Ibrahim, it is true though that if you make the plate bigger, the plate, you do increase the capacitance. If you make the area bigger. So another choice is or increase area A. So by area I mean, if I draw this here, this is what I mean by area A. No, the distance needs to be smaller to make the capacitance bigger. Yes, yeah, the material as well. I think, can't really, I don't think it matters too much once you're using some good conductor like copper. Yeah?
So if the area is large?
If the area is large, you can hold more charge, you get more capacitance, yeah. But what's strange is, in fact, if you make the distance smaller, it makes the charge bigger. You can hold more charge.
So which way is more accurate?
I would say the area. No, it's about the same actually, because what will happen is if you make the area twice as big, you make the capacitance twice as big. But if you half the distance, you make the capacitance twice as big. I can tell you which is cheaper. Which is cheaper? Make the distance smaller, because you can do that for free. So I think if you're asking me which is more effective, you probably want to try and reduce the distance. But you have to be careful, okay? It's very important that the plates don't touch. So if the plates touch, then no more capacitor, okay? So you want the plates to be very close, but don't touch, okay? Right.
Yep.
What's that? You can make it yourself. What you need is like one piece of copper and then another piece of copper and have them very close together, but don't touch. And that's it. That's the capacitor. Yeah. Oh yeah, well then what you do is you plug it into a battery and then it charges up.
You're saying a vacuum.
A vacuum is nice, but not necessary. Yeah, what are you saying?
The electrons move faster.
Yeah. What are you going to ask me?
And then what's the distance is the code you plan to.
If you can make the distance smaller, you can make it better. Yes.
Use what material?
Material? Just copper will do. You know copper? Copper,
Wires, there's no wires.
copper.
So why?
Wire.
What is it? AU, is it?
No, it's
CU? I use gold, yeah. But gold will work as well. Copper will do. Copper is, do we have any, you know copper, it's brown, isn't it? Yeah. And why else might you use capacitors? Well, Ugo suggested it in electrical appliances. And this is true as well. I'll give you an example, like with your computer. So you know inside your computer you have something called a CPU, you know CPU, the processor. So for example, my processor is Intel Atom, for example. Okay? Now, what you can do sometimes here is you can put a capacitor connected to the processor. And the purpose for doing this is if the voltage suddenly increases, then what happens is the capacitor suddenly charges quickly. So you get a lot of charge here. But it doesn't really cause an increase in the voltage after the capacitor. In other words, the capacitor can act like a speed bump. So you have your voltage, and if it suddenly increases, what it does is it charges the capacitor up. Charge the capacitor up quickly, you know. Now, okay, this isn't completely true. I'm making it too simple here. I'm making my diagram too simple. But the idea is still true, that you can use a capacitor to get the extra charge if you have too much. Okay? And then likewise, like you said, Ugo, if the battery drops a little bit, then the capacitor could release its extra charge. So in other words, the capacitor can try and help to balance the charge. When you have too much charge, the capacitor can take it, and then when you have too little charge, the capacitor can release it. Now my diagram is too simple, okay? But it just gives you the idea. The capacitor is useful this way. What other uses can we have for capacitors? Let me think. We have for the heart, we have for the camera. Oh yeah, and of course for the police gun. You know, the electric gun the police use? You know what I'm talking about? You know it? Do you know what I'm talking about? The gun the policemen have where they shock you. Yeah? I'll try it. Tasers, yeah. It looks like this, doesn't it? Yeah. And then they shock you with it. Yeah. So inside of this is a battery, and then there's a capacitor. So what happens is the battery charges the capacitor, so you get lots of charge, and then when you press the button, the charge then is released across these 2 points from the capacitor. Yeah? What else do we have? I think that's mostly it really for capacitors. We're going to talk more about capacitors in the next class. So for today we just have one capacitor, but tomorrow we'll look at when we put capacitors together. You know, if we connect the capacitors together. A bit like when we connect the resistors together. Okay, we can connect the capacitors together. But we'll talk about that. We'll talk about that in the class tomorrow. So if you go to the next page. I don't think you need to do number 1. It's okay. So yeah. So you can just start at number 2. It is, it's from physics now. If you start from number 2.
What are the start rules?
That means they're more difficult.
I think it's, I thought they meant the experiments.
You thought they were what?
The experiments, because the first 2 describe the experiments.
No, the stars just are for more difficult. So if you can start with number 2. So number 2, I give you the capacitance, and I give you the voltage, and what do I ask for? Oh no, sorry, I give you the charge, and I give you the voltage, and I want the capacitance. So it's okay, isn't it?
And then it's given from to the capacitor.
Yeah, well I've given you a few there. Okay, so try these now for a few minutes please. 2 to 11.